So I want to begin with a cartoon that maybe many of you have seen. It's an XKCD cartoon. And the protagonist runs in at the beginning and proposes that maybe jelly beans cause acne. And the scientists are exhorted to investigate. And they find, no, they cannot find evidence that jelly beans cause acne to a level of significance p less than or equal to 0.05. But then it's proposed that maybe actually it's just one color of jelly bean, and then there's 20 colors of jelly beans out there. So they check every single one of them. They run a hypothesis test on every single one of them. And for exactly one of them, for green jelly beans, they find that there is a statistically significant connection between green jelly beans and acne at a level of significance at p less than or equal to 0.05. And so there's this front page article that's published, only a 5% chance of a coincidence. So, we need to account for multiple comparisons. If you test 20 things, it's not surprising that one of them is significant at a 5% level of significance. And so the underlying problem is that we care about the effect of jelly beans on acne in some underlying distribution, but we only see samples. And so really what we should do is we should affix confidence intervals around any kind of statistic that we estimate, because we're estimating it in sample, we care about it out of sample. And of course, we all know if we've treated, if we've had k test groups, one for each jelly bean, and in each one we've treated n people, then our estimate of the probability that a participant in each jelly bean treatment group will develop acne will have error, and we can bound that error with a Chernoff bound and a union bound, then it'll scale roughly like square root of log the number of jelly beans divided by n. So we get this very nice scaling where we only have to correct for sort of something on the order of square root of log of the number of things we've tested. But things get much worse if the tests that we make are adaptive. So just to sort of make that crystal clear, let's go through a toy prediction example. Suppose we've got some data set that's got a bunch of binary features. So whether you're married, whether you have a college degree, things like that. And we're trying to predict some binary feature as well. And let's imagine that we've got a simple class of models. So for example, a model might be defined by some subset of the relevant features. So a model might be defined by the features has a college degree, has children, your marital status, and there's 2 to the d models here because there's 2 to the d subsets of features. And the classifier in this toy example is just going to be a majority vote over the relevant features. So if we're just going to predict that the label is +1 if at least half of the relevant features are +1, otherwise we'll predict -1. Right, so because there's 2 to the d models here, if we want to estimate the error of all of them, then we've got to correct for that. And this is sort of the jelly bean problem times 2 to the d. We've got like 2 to the d things we're estimating. But when you learn a model, you don't actually enumerate all of them and evaluate the error of that model independently. Instead, you sort of do something more efficient. And so let's just go through a little example. Suppose we're in a setting where actually all of the features and the label also are uniformly random and uncorrelated. So it's not actually possible to predict anything. Here's a way with only d queries rather than 2 to the d queries that I could find the classifier that performs the best on the data, which of course will be the worst overfitting classifier on the distribution. For each of the features, I'm just going to query what is the correlation of that feature with the label? Just what is the inner product of the column corresponding to that feature with the column corresponding to the label? And if it's positive, I will say this is a relevant feature, and I will add it to my set. And if it's negative, I won't. And in the end, I've got some model that I've learned. I've added some relevant features to my set, and I'll just ask the query, what is the error of my classifier? And what you get is that this has actually found the sort of worst classifier. I'm paying the full cost of having evaluated all of the 2 to the d models in that my error, and remember in the non-adaptive case, the error scales with square root of log of the number of things I've tested. Here I'm paying for that already, even though I haven't explicitly tested all of them, right? I'm paying for square root of d in my error term, which is like log of 2 to the d. But this is even though I've only actually asked d queries about the data. The issue was the last one was adaptive. I chose which model to evaluate on the basis of the evaluation of the previous queries. And this is actually the sort of worst case example, at least if we answer these queries with bounded bit precision and don't allow like floating point games or something. Now here we actually know the process, right? So you could say, okay, well, like, what you should have done is corrected for all of the 2 to the d models, but this is much more insidious if the process is informal. So here's an article in BuzzFeed you might have seen about Brian Wansink, who was a prominent food scientist at Cornell until this article was published. And BuzzFeed was able to get access through a Freedom of Information request to many of Brian Wansink's emails. By the way, even if you don't work at a public university, if you correspond with people who do, you should expect the possibility that BuzzFeed might eventually get a hold of your emails. And Dr. Wansink was investigating basic science about half-price buffets, and here was a correspondence between him and a young researcher who was joining his lab. He was instructing them on how to dig into the data. And he says, well, you don't really know what you're looking for until you see the data, right? We want to know how half-price buffets affect people's behavior. There's many kinds of people, so you shouldn't just consider them all, consider men, consider women, consider people who are going for lunch, for dinner, people sitting alone, people in groups of 2, people in groups of 3, and so on. And we don't really know what we're looking for. So for each of these groups of people, let's think about how many pieces of pizza they ate, how many trips they made to the buffet, the fill level of their plate, and so on. And this is really the same process that we sort of just described in this worst case example, but now it's like hard to get a handle on the possible multiplicity of models because it's a human being doing this, and we've got words like and so on. And for the same reason, if someone's doing this, you cannot just correct for multiple hypothesis testing by enumerating the number of things they've actually investigated. In principle, you have to correct for all of the things they might have investigated had things turned out differently. So how do we do this? All right, brief interlude. Differential privacy, you might have heard of it. It was introduced 15 years ago now by Dwork, McSherry, Nissim, and Smith. And it is a sensitivity constraint on an algorithm. It sort of says, okay, well, if I've got some randomized algorithm and it induces some distribution over outputs, then if I change just one person in the input data set, this should change the output distribution only by a little bit. So a little more formally, if we think of a data set as some n-tuple of records from some data domain, let me use the following notation to write d minus I xi prime to mean the same data set. If I remove the ith record and swap it out for this other version of it, I've taken out xi and I've plugged in xi prime. Okay, I'll call this a neighboring data set, one that differs in a single element. So we'll say that an algorithm is differentially private if for every data set, and for every data set that might neighbor it, anything I can get by swapping out one element for another, and for any event E, any subset of the outcome space, if I look at the probability of this event E when I run the algorithm on data set D, and I look at it when I run the algorithm on data set D prime, this neighboring data set, then these probabilities should be related. And if delta is 0, we'll call this epsilon differential privacy, and it's really just bounding the odds ratio, the relative probability of this event under the experiment when I run it on D versus the experiment when I run it on D prime. And sometimes we'll allow a delta, which is just this small additive correction here. Okay. So like if there's one thing to know about differential privacy for this talk, it's that it composes adaptively. So here's what I mean by that. Here's some experiment called adaptive k-fold composition, where we can have an arbitrary adversary. And what they're going to do in k rounds is the following. They are going to look at the outcome of all of the mechanisms that have been run so far. Based on that, they are going to choose a new mechanism, a new algorithm, only under the constraint that the new algorithm they choose has to be differentially private, and they're going to run it. Okay, so the adversary is adaptively making choices as a function of the outcome of the mechanisms he or she has previously run. And at the end, we'll output the entire sort of transcript of this experiment, the sequence of mechanisms that were chosen and the sequence of outcomes. And The nice thing about differential privacy, this version of the composition theorem was first proven, I guess, 11 years ago now by Dwork, Rothblum, and Vadan, is that this adaptive composition experiment is also differentially private, and the differential privacy parameter degrades in this sort of nice sublinear way, right? If the original mechanisms had privacy parameter epsilon, then this composition has privacy parameter that is worse by an amount that is not like linear in the number of rounds k, but only with the square root of the number of rounds k. Okay. So the nice thing is that an adversary can choose how to compose these mechanisms, and we get this sort of nice, graceful, sublinear degradation in the privacy parameter. All right, so the privacy parameter degrades sublinearly with k, and the adversary can really be anything, and so could be a human data analyst. And so, like, having gotten to this point in the talk, it is natural to ask, might this be useful for adaptive data reuse? And here's a formalization of adaptive data reuse. Okay, we've got some data set. It's initially drawn from some distribution. So it's endpoints that are drawn IID from some unknown distribution. And now we've got an experiment that looks a lot like adaptive composition. Okay, for k rounds, we've got an arbitrary data analyst who could be an adversary. And what they are going to do is they are going to adaptively choose queries to ask about the data distribution as a function of what has happened before. The semantics of a query, which is just some function that evaluates to some number between 0 and 1 on each data point, is just what is the expected value of this predicate on the data distribution. And the curator gets to look at this query, gets to look at the data set that was initially sampled from this distribution and potentially the whole history, and propose some answer. And after k rounds, we will evaluate how well the analyst did by asking what is the max error, the worst error of any query asked with respect to the underlying distribution. So we'll evaluate the analyst by asking what is the biggest difference for any answer that the analyst proposed compared to the real answer, which is the expected value of this query on the underlying distribution. And our goal is to design a curator that minimizes the error for a worst case data analyst. Okay. So the core of the connection between differential privacy and adaptive data analysis is this transfer theorem. And this is something we first proved in STOC 2015 with Dwork and Feldman and Hart and Patasi and Reingold. With a not super elegant proof, this was basically direct calculation and the rates were suboptimal. And then in STOC 2016, there was this beautiful paper by Basili, Nissim, Smith, Steinke, Stemmer, and Ullman that introduced the ingenious monitor argument. It's found other uses. It's really pretty. You should read this paper that got the optimal rates, but got sort of bad constants. Okay. And what is the transfer theorem? Well, forget the parameters for a moment, because we're going to prove a sort of tighter version of it. But it sort of says, if you can design a curator that is differentially private on the one hand, and on the other hand is sample accurate, that provides answers that are accurate just with respect to the sample, not with respect to the distribution. So this is purely an algorithmic task now, not a statistical task. Right? If you can be both differentially private and accurate in sample, then with high probability, you are also accurate out of sample. That's the core of the theorem. And what I want to do in the remaining time is show you how you can prove like a pretty tight version of this theorem without doing any math at all, basically. But like there's a really, really simple proof of this theorem. Okay. So the first thing I want you to do is to sort of conduct a thought experiment. Okay, so here's our adaptive data analysis scenario. Remember, a data set is sampled, and then an analyst in k rounds adaptively chooses queries to ask of the mechanism, and the curator answers them. The new thing in this thought experiment, something that's not really happening, is that every round, after the curator provides an answer to the data analyst, we are going to imagine that the data set is freshly resampled. Okay, so instead of the data set being fixed now, it's freshly resampled every round, not from its sort of underlying original distribution, not from its prior distribution, but instead we'll resample it from its conditional distribution, the conditional data distribution, conditional on everything the analyst has seen so far. Okay, that's the only difference. In this thought experiment, every time a query is answered, we resample the data set from this like conditional data distribution. And the observation is that this thought experiment leaves the joint distribution on queries, data sets, and answers unchanged, right? Like as a general rule, you can always imagine resampling any random quantity from its conditional distribution, conditional on everything you know. And so things like accuracy, right? Those are properties of this joint distribution. And so we might as well proceed by analyzing this thought experiment instead of the original experiment. And so how's the analysis going to work? Well, on the left-hand side here, we've got the answers that our mechanism has actually provided. On the right-hand side, we've got the real values, the real answers to these queries, which are just the expected value of the queries on the underlying data distribution. And in the middle, we've got this new quantity that's been introduced by our thought experiment, which is the expected value of the query, not on the original distribution, but on the conditional distribution, conditional on everything we've learned. And what we're going to argue is that on the one hand, the guarantee of sample accuracy, the fact that our mechanism provides answers that are accurate with respect to the underlying data set, means that the answers our mechanism provides must be close to the expected value of the query on the conditional data distribution. And if you think about it, this is sort of inevitable once you are thinking about this thought experiment, because the mechanism is first committing to these answers, and only then is the data set being resampled from this conditional distribution. So the only way that the mechanism can promise that these answers are going to be close to the empirical value of the query on this data set that hasn't even been sampled yet is if it's close to the expected value from the sampling distribution. This is going to follow from sample accuracy. And differential privacy will relatively immediately tell us that the expected value of the query on this conditional distribution is close to the expected value of the query on the original unconditional distribution. And putting these together will give us our theorem. Okay, so two claims. First, if the curator is sample accurate, meaning with high probability it gives answers that are close to the empirical answers on the underlying data set, then it must be that with high probability over the randomness of the whole experiment, that if I look at the worst case difference between the answers our mechanism has provided and their expected value on the conditional data distribution, conditional on the transcript of this experiment, those have to be close. And again, this is sort of almost immediate, right? Sample accuracy still holds under this resampling thought experiment because the resampling thought experiment hasn't changed the observable distribution at all. And so, the only way the answers can be guaranteed to be accurate on the data set that has yet to be sampled is if they are accurate in expectation over the distribution that it will be sampled from. And so you get this just by applying Markov's inequality to the resampling distribution. There's nothing special about the number 2. You can replace that with a C and get a slightly more general statement. Okay, second, if the curator was epsilon differentially private, then for any query at all, if I look at the expected value of this query on the original distribution, the thing that I really care about, the real answer to the query, and I compare that to the expected value of the query on the conditional data distribution, those things also have to be close within an e to the epsilon minus 1 factor. And this is almost immediate from differential privacy. It's like 2 lines. I'll just prove it to you right now. So we've got some arbitrary mechanism. All we know about it is that it's differentially private. Let's think about the probability mass under the conditional data distribution, conditional on the output of that private mechanism of any particular point x. Well, I can just apply Bayes' rule, and I can relate that to the probability mass of the same point x on the underlying data distribution. And it's related just by this Bayes factor, the sort of increase, the relative increase in probability of observing some outcome pi from the mechanism, conditional on the fact that the ith point in the data set was x. And I can expand out that Bayes factor and see that it just sort of looks like the sort of log, or it just looks like the odds ratio of this differentially private mechanism, okay? The odds ratio that this differentially private mechanism outputs some point pi when on the one hand, it's run on some data set in which the ith element is X, and on the other hand, it's run on some data sets in which the ith element is something else. And this is exactly what differential privacy bounds. And so the probability masses pointwise on the original distribution and on the conditional distribution are close within an e to the epsilon factor, and that gives the lemma. Now that was for epsilon 0 privacy. The same thing is true for epsilon delta privacy. You know, instead of being like 3 lines of algebra, it's like 10 lines of algebra. I won't go through it, you know, but this is what it looks like in the paper. You know, conceptually, it's not much more complicated. And then, you know, once you have those two claims, that's it, right? You just glue them together with a union bound, right? This is just a triangle inequality, right? Like, you know, with high probability, the answers are close to the conditional expectation of the answers. And also with high probability, the conditional expectation of the answers are close to the expectation of the answers, the real answers. And that's it. So you get this transfer theorem having hardly done any math at all. So, you know, let me say a couple more things about it. So first of all, like what are transfer theorems like this doing? They are reducing a statistical problem to an algorithm design problem, right? The original problem we want to solve is statistical. We're talking about sort of out of sample error. What this is saying is it is sufficient to solve an algorithm design problem to design algorithms that are differentially private and accurate in sample. There's no statistical problem here. And fortunately, this is a problem that we've already been working on. There's like 15 years of research on this. And there's many ways to do it. The simplest one is just to perturb the answers to these queries evaluated, you know, empirically on the data set with Gaussian noise. And let me use that mechanism to try to sort of compare quantitatively these different versions of the transfer theorem. So there's different ways to compare these bounds, but here's one. So suppose I say, okay, I would like to be able to affix the answers that I give the data analyst with confidence intervals that have coverage probability 95% and width at most 0.1. And then for each of these bounds, I can ask, okay, well, how many queries can I answer before the theorem fails to promise this guarantee? And so the answer will be different for different data set sizes. So on the x-axis here, we have growing data set sizes, growing larger and larger, and we can answer more queries the bigger our data set size is. On the y-axis, we have for each data set size, how many of these queries can we actually answer before our theorems fail to promise this guarantee? And there's a natural baseline to compare to, which is just sample splitting. Right, so if you've heard of using a holdout set in machine learning, that's the special case of sample splitting when k is 2. But another thing I can do is if I'm going to answer k queries, I will just chop my data set of size n up into k data sets, each of size n over k, and use a fresh data set for each query that comes in. So it just removes the adaptivity, and that's a baseline. And you know, this dotted black line here is sort of how many queries you can answer using the baseline. It grows only linearly. Now, our original theorem, this is from STOC 2015, you know, it's this like green line that seems not even to be growing at the bottom. Like we can take n all the way as large as 1.6 million, and like we haven't seen any movement here. It definitely isn't beating the baseline. This sort of asymptotically optimal bound with this beautiful monitor argument from STOC 2016, that's this dotted red line, you start to see some movement here. You can sort of see that it's quadratic. It'll eventually beat the baseline. And it does eventually beat the baseline at around 1.2 million. And this new bound we proved, which has the same asymptotics, by the way, as the red bound. You can't beat the asymptotics of the red bound. It's optimal. But this new bound we proved, essentially without having to do math, it's this blue line. And just sort of quantitatively, if you think about like the constants, this is performing much better. Okay. So I'm just about out of time. Simple argument, better constants. I think some interesting structural insight. This conditional data distribution is the right thing to think about. And there's some interesting open questions. In particular, for those of you that know about it, can you get max information bounds via a similarly simple argument? And with that, let me end.